Guys, so let's go ahead and talk about intermolecular forces. Okay, so we've talked about intramolecular forces, talking about ionic and covalent bonds, which are the bonds within a single molecule, but we want to talk about intermolecular forces, or the forces between multiple molecules or formula units and atoms. Okay, so we know that you're never really looking at just one molecule. You're looking at multiple molecules that are kind of sharing neighboring space with each other. And so the first thing we're going to talk about is ionic intermolecular forces. So there is obviously going to be this attraction between a single chlorine and a single sodium atom, like in this image here. But it's also going to have an ionic attraction with the ones around it. And so what happens when you do that, you can see it's kind of making a square, is it's going to make this crystal lattice structure. And this is an extremely strong attraction. In fact, it's going to be the strongest of them. So any type of ionic compound, so anything that has a metal and a nonmetal or has a polyatomic ion, will have ionic forces in there. And it's just that attraction between the negative and positive ions. Now, when we're looking at covalent compounds, we're going to be looking at three other types. So let's look at the first one. Scroll. There we go. So the first one we're going to talk about is dipole-dipole forces, or attraction. And so when we're talking about dipole-dipole forces, these forces are going to be between polar compounds, so polar covalent compounds. And so one way we can look at that is if we look at HCl. Okay, to know whether or not something is polar covalent, we're going to need to look at its delta electronegativity values. So if we look over here on this little box, we see that chlorine has a stronger electronegativity, or a higher electronegativity, than hydrogen. We also know that hydrogen naturally is going to be a little more positively charged. Chlorine is more negative. And so what we see is that chlorine has a partial negative, so that little symbol that I drew there means partial. So this right here means partial. And hydrogen is going to be partially positive. It's not fully positive or fully negative like in an ionic compound, but because of the difference in their electronegativity values, so if we look at their delta electronegativity values, we get 3.1 minus 2.1, which gives us 1.0, which lands us squarely in the polar covalent range. Remember, you need to have anywhere from 0.4 to 1.7 in order to be polar covalent. And so what we see is that all of these hydrogens, they're going to be partially positive, and that's because the electronegativity of the chlorine means that those electrons are going to be spending a lot more time. They're going to be more densely populated around that chlorine instead of the hydrogen, which we can see because there are 6 lone pairs of electrons around each chlorine, and then there's only 2 that are shared between them. So chlorine is going to have a lot more electron density. It's going to be partially negative. Now, when this happens, okay, a partial negative and a partial positive, when they get near each other, they're going to form an attraction. And so this is kind of an intermolecular force. So this dotted orange that I'm drawing is showing that this partial negative and this partial positive are going to be attracted to each other, and it's going to create a strong bond. And one thing to keep in mind is the stronger the intermolecular force, so the IMF, the higher the melting point. Okay, so anytime you're looking at melting or boiling points, or really any sort of physical feature, it's all going to come down to its intermolecular forces, or IMFs. Okay, so dipole-dipole are pretty strong. But a special type of dipole-dipole is hydrogen bonding. Okay, and so the key phrase to remember is that hydrogens just want to have fun. And obviously I'm not saying fun like in the song, but hydrogens just want to have fun. So it's talking about fluorine, oxygen, and nitrogen. So if you have molecules where there are going to be hydrogens and nitrogens available, you're going to see a special type of bond. Because if we look at oxygen, oxygen is going to be partially negative. Hydrogens are, again, are partially positive. And so you're going to see, and nitrogen will be partially negative, you're going to see a strong attraction. And because oxygen, fluorine, and nitrogen are very small, they can get really close together. And so this intermolecular, oops, sorry, drawing it to the wrong space. If we were to have another water molecule here, right near it, okay, that is also partially negative, we're going to see that this partially negative charge is going to form a very strong dipole-dipole bond called a hydrogen bond. And because oxygen and hydrogen are so small, they can get very close together. And so this is the strongest intermolecular force besides ionic. Okay, ionic is not really an intermolecular force because when it's all together, those ions are kind of mushed in one place. But hydrogen bonding, strongest. Then you're going to have dipole-dipole, and the weakest of them all are the London dispersion forces. These are found in all molecules, and they're the weakest. Okay, so essentially what it's saying is these electrons that are in these bonds here, okay, they're kind of moving around and they're shifting, so it's going to cause a temporary dipole or temporary charge. Okay, so we talk about how oxygen is partially negative and hydrogens are partially positive because of the difference in electronegativity. But London dispersion forces, I mean, if we look at the difference between carbon and hydrogen, carbon is 2.5, hydrogen is 2.1, you get 0.4. I mean, that's very close to being completely nonpolar. And so the difference between those is not going to be that great, but electrons are always moving, so it's kind of going to shift. The main time that London dispersion forces are really going to show up is when you have larger molecules like this one over here. So, oops, I forgot my valence electrons on these oxygens. But when you're looking at this molecule, we have a lot more bonds being formed. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bonds and 8 lone pairs of electrons. So you have a lot more electrons that are moving around, so your density is going, your electron density is going to shift more often. So that temporary dipole is going to be a little bit stronger. Plus, we also have oxygens in this molecule, oxygens and hydrogens, so you're going to have hydrogen bonding as well in this molecule. So one thing that you might need to look at is how to tell all of these things. So let's say we have a few molecules. So this was the warm-up in class this morning, was you had to look at H2O, NaOH, which all NaOH is a solid at room temperature, H2O is a liquid, H2S, which is also a liquid, and O2 gas, because remember oxygen is diatomic, and this is talking about at room temperature. So if we're looking at these and trying to decide, okay, what type of forces are present? Well, for H2O, we would say, well, we're going to have London dispersion forces, okay, because it's going to be covalent. We have all nonmetals, and we have hydrogen and oxygen both. So that means we're going to have hydrogen bonding, and we know it's polar because oxygen is 3.5 minus 2.1 gives us 1.4. So we're also going to have dipole. Whereas NaOH, because sodium is a metal, so this is sodium hydroxide, we're going to have ionic bonds. in there. It is an ionic compound. H2S is going to have London dispersion forces. Sulfur is around 3.0, and hydrogen is 2.1, so you get 0.9, okay? So you're still polar covalent, not as polar as water is, but still pretty polar. So you're going to have dipole-dipole bond in there, but you're not going to have hydrogen bonds because we have hydrogen, but we don't have fluorine, oxygen, or nitrogen. And then oxygen is 3.5 minus 3.5, which will give you 0. So this is non-polar. So that means it cannot have hydrogen bonding or dipole-dipole. It will just have London dispersion forces. And so being able to identify these forces really gives us insight into why they have the states of matter that they do. Okay, so if we look at their states of matter, which I'm kind of putting in a box in purple right now, okay, we know ionic bonds are the strongest, and what do you know? It is a solid. Okay, if you have really strong bonds, you're going to need more than the temperature in the air, or the energy that is the temperature, in order to break those bonds and turn it into a liquid or a gas. So these are going to be the strongest. And if we look at, okay, well, what's going to be number 2, right? Well, if we look at H2O and H2S, they're both liquids, so they're the next, I guess, together phase, right? Solids, the atoms are very close together, liquids are a little further apart. Oxygens are, or excuse me, gases are the furthest spread apart because they're not really going to feel those intermolecular forces. And so if we're looking at water and hydrogen sulfide, we see that the only difference is that water has hydrogen bonding, and so that's going to make it number 2 because hydrogen bonding is extremely strong. And then H2S will be number 3, and oxygen only has London dispersion forces. It's a very small molecule with only 2 atoms, so it's really not going to be that strong at all, which is why it's a gas. The energy in the air at room temperature is plenty to break those intermolecular forces and keep those oxygen molecules very separate. So I hope that this helps you summarize and kind of see what's going on. You will need to make sure that you can talk about all these things tomorrow for your DBQ. So good luck.